So today we're going to be doing lesson 3.9, which is roots and zeros. This is the last section that will be covered on your test next week. As you guys know, you have a quiz today. The quiz will not cover this topic because, not everybody has learned it by the time the quiz opens. The quiz will be open from Thursday after school today to Sunday night. So let's get started on the lesson. So the fundamental theorem of algebra states that every polynomial of degree n has n complex roots. These complex roots can be real roots only, imaginary roots only, or a combination of both real and imaginary roots. So you guys already know that. If the degree of the polynomial is 4, how many roots do we have? 4. It's always the same as the number of roots that you have, the degree of the polynomial. And those roots can be comprised of real or imaginary or complex roots. And then the complex conjugate theorem states that if a plus bi is a root of a polynomial, then its conjugate a minus bi is also a root of the polynomial. In other words, complex conjugate roots are always found in pairs. So I know we've talked about this a lot. You know how when you find an imaginary number, you always do so by taking the square root of something. Anytime that you take the square root of a negative or any number, you have a plus or minus. So basically, imaginary roots always come in pairs, one being negative, one being positive. So that's basically what this theorem is reiterating to you guys. So we've talked about it in passing, but we hadn't addressed what it's called. So that's what this theorem states. So now we're going to refresh on multiplicity. So the number of times a polynomial's linear factor occurs is what we call multiplicity. So in this case, what's the multiplicity of x plus 3 as a root? Because it occurs how many times? Yes, it occurs twice, so its multiplicity is 2. And then the other roots only have a multiplicity of 1 each. So it's important just to recognize that because multiplicity changes how a root looks on the graph. And since today we're going to be graph sketching and graph interpreting, it's important to understand that. So odd multiplicity, anytime your multiplicity is odd, that means that the line or the function crosses your x-axis at that point. And if we have an even multiplicity, it touches it, but it doesn't actually cross it. It actually bounces on it. So that's a really important concept today that we're going to talk about because you have to be able to understand what the graph is telling you and sometimes sketch your own graph. So let's go ahead and do an example together where we're going to look at all the polynomial characteristics and identify what we can about this polynomial. So the first thing you always want to look at is the number of turning points. How many turning points are there on this graph? 3 turning points. That's the letter E that you're going to label here. 3 turning points. And does anyone remember the relationship between turning points and the degree of the polynomial? Add 1. So the degree of the polynomial is 4. That's the answer to letter B. Sometimes we go a little out of order just for the sake of what information comes at us as we go through the problem. And then we want to classify the polynomial. So as you know, different polynomials of different degrees have different words to describe them. Anybody remember what a 4th degree polynomial is called? Not quadratic, but quartic. Very good, guys. So that's what we call a 4th degree polynomial. We call it quartic. And it's been a while, but the next thing we're going to talk about is end behavior. So in this case, on both sides, my polynomial is going up. So it's positive infinity. It's going to positive infinity on the left, and it's also going to positive infinity on my right. Okay? So my end behavior is upward and upward, which makes sense because it is even. And is my leading coefficient positive or negative? Positive, because we ended upward and upward. If you don't remember end behavior, there's a chart on your 4-1 notes. I believe it's 4-1. That chart, remember with the dancing guy, where it tells you the directions? That's what I'm referring to here. And the next thing we're going to look at is zeros. So zeros are where we cross the what axis? X-axis. Very good. So we're going to find all of the times where my graph crosses the x-axis. And how many times is that? 3. And we're going to give the coordinates of each of those. So -4, 0. -2, 0, and 3, 0. Those are the 3 times my graph crosses the x-axis. Now we're going to determine the multiplicity of each of those. So for -4 and -2, the line or the graph goes straight through, right? So the multiplicity is 1. And the behavior is it crosses the x-axis. But something different occurs at the 3. What happens at the 3 that's different than the others? It bounces. And what do you think my multiplicity is here? 2. Even multiplicity always bounces. So as you get into higher and higher multiplicities, it gets harder to identify visually. So I'm mainly going to ask you to identify 1, 2, and 3. Those are the main types of multiplicity you'll have to visually identify. And then we're going to talk about maximums and minimums. So graphs can have absolute maximums, absolute minimums, and then they also have relative or local maximums and minimums. So let's talk about what that means. So a relative maximum is basically any low point on your graph, any valley on your graph. Okay, I'm sorry, any hill on your graph is a maximum. Minimums are the valleys. So our relative minimum is this right here. Now, it kind of looks like it's at 0, 3, but it's actually at like 0.25, 3. You guys see that right here? Our relative maximum, that's right there. So it occurs at about 0.253, maybe 0.5. Some of these aren't particularly accurate, so just do your best. And then we're going to talk about our relative minimums. So we actually have 2 of those, right? We have one right here, and we have one right here. So it looks like our relative minimums are at, I think that's at about 3. It looks like it's like -3.25, comma, about -1.5, would you guys say? And the other one is at 3.1. I'm sorry, not 3.1, 3.0. So that's from these 2 coordinates. Now these are your relative minimums, but is one of these also the absolute minimum? Yeah, because isn't this the lowest that my graph ever goes? So this is also my absolute minimum. So it's important to note that there's not an extra line for it. I wish there was. I should have adapted this, but that's the idea. That's our absolute minimum. Do we have an absolute maximum on this graph? No absolute maximum, so we don't have anything to write. Because this graph goes on forever in the upward direction, meaning there is no absolute maximum. So basically it just says label the graph using characteristics listed. This should say E, not C. E, F, and G. So we basically already did that. We circled the number of turning points. For F, we labeled our x-intercepts. And for G, we put dots on our maximums and minimums. So that's basically, we already did everything that they asked us to do. It's just basically wanted you to note that stuff on the graph. And then the last part is to write the polynomial in factored form. So you do this by writing f of x, or whatever you want to call it, g of x, or you could even say y, is equal to. Now you have to work backwards from the zeros. First thing you always check is your leading coefficient positive or negative? Positive. So the beginning of it, is it going to be positive or negative? Positive. Positive. So you don't have to put a negative sign in front of anything. If you had negative, you'd have to put a negative sign right here. We don't have to. Then you interpret by taking your zeros and turning them into binomials. So what would -4, 0 be as a binomial? X plus 4. It's always the opposite. Okay? That comes from this right here. And then next, it would be x plus 2. That's this one. And then lastly, it would be x minus 3. That comes from this one. The only difference is, how many times does this 0 occur? Twice. So what do I have to do to this one? Put it to the second power, because the multiplicity is 2. Multiplicity tells you what the power of each binomial is. So that would be your polynomial. And if you put this in Desmos, you get a general sketch of what this looks like. It might not look exact but it will give you the same hills, valleys, and behavior. Any questions on this so far? You guys feel good about this? Okay. Let's try another example. So the first thing I always identify is my number of turning points. So I have a turning point here, 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 and here. So you guys see 4 turning points on that? You guys see all 4? So the number of turning points is 4. So that means that the degree of my polynomial must be 5, always one more than the number of turning points. Now we're going to classify our polynomial. What do we call a polynomial to the 5th degree? Quintic. So this is a quintic polynomial. Now we're looking at our end behavior. So you can put arrowheads on it if it helps you visualize it. On the left side of my graph, as x goes to negative infinity, what does my function do? Down or up on the left? Down. It goes down to negative infinity. And on the right side of my graph, where x is going to the positive values, is my function going up or down? Up. Next, we're going to determine what the sign of the leading coefficient is, which is determined by your end behavior. This graph starts down and ends up. This is odd. Anybody remember odd positive or odd negative from your end behavior lesson? Odd positive. So if you don't remember, that's the chart I'm referring to. So that means the coefficient in the front of your polynomial, if you had the equation, would be positive. Now we're going to state our zeros. How many zeros do you guys see on the graph? 3 of them. Here, here, and here, right? So let's go ahead and list those coordinates out. So it looks like we have negative 5, 0. We have negative 1, 0. And we have 3, 0. Everybody agree with that and see that on the graph? Now we're going to determine the multiplicity of each of these. So what do you think about the multiplicity of the negative 5, 0? 2. Does everybody see why it's 2 and why it's not 1 right here? It doesn't, and instead, does it cross through or does it bounce? Bounces. Doesn't cross through, it bounces. Okay. So, next we're going to look at the multiplicity of negative 1. What do you guys think? Good, 2. And it bounces. And what about the multiplicity of 3, 0? 1. And what does it do here? Crosses. Very good. Okay. So next, we are going to look at the relative maximums and minimums. So these are basically any turning points on your graph. So how many relative maximums do you guys see? 2. And the coordinates for those are negative 5, 0 and negative 1, 0. Do you guys all see those relative maximums, those hills? Hills are relative maximums. Didn't that sound like it went on for like ever? It's like, I swear it gets longer every day. They just like add another beep in and we just don't know about it. Okay, anyways. I get so distracted with them. I imagine you guys too. And then the relative minimums. You guys see both of those relative minimums? One of them looks like it occurs at about negative 3, would you guys say? Negative 3, negative 3. Right here. It's not exact, but about that. And then the other one occurs at 2, negative 17, would you guys say? Everybody see where I'm getting those from, those coordinates? We're just kind of eyeballing it because it doesn't really give us any grid. So, are either of these relative maximums? And I record this period too. Are either of these relative maximums or minimums also absolute? No. Why are neither of them absolute? Good, my graph goes up and down forever, so no absolutes. And then we already did this, it's label E, F, and G. Well, we already did that. We already labeled the turning points, we labeled the zeros, and we also labeled the relative maximums and the relative minimums. So just make sure you understand where those come from and how to interpret them. And then we're just going to write our polynomial in factored form. So it's going to be f of x equals, now first thing you look at is, was your leading coefficient positive or negative? Positive, so you don't have to put a negative sign out front. If you did, if it was negative, you'd put a negative sign out in the front. And then you just look at the zeros, so it's going to be x plus 5 to the, good, to the second power because of the multiplicity, times x plus 1 to the second power because of the multiplicity, and then 3, or x minus 3, and is that going to be to the second power? No, because that 0 only occurs once. So this would be your polynomial if you were to graph it in Desmos, which we'll try. So I went ahead and I just graphed this. So as you can see, it has the same characteristics as ours. It's just a lot bigger, but it has that same movement. So it goes up, down, up, and then it comes back up. You guys see the similarities there? It's just ours is more like stretched out. So you can always check on Desmos to make sure it has all the same turning points. But obviously the magnitude and like the stretch of it is going to be a little different on Desmos. You guys ready for the next one? Okay. So now we're going to talk about sketching a polynomial. So the first thing you always want to do when you sketch a polynomial is to determine the degree of the polynomial. So, well, how you determine the degree is how many zeros do you have? How many zeros do we have here? We don't have 3, we actually have 4. Everybody see how we have 4 zeros there and not 3? Because this one's to the second power, which means that really we have y equals x plus 2 times x minus 1 times x minus 1 again times x minus 3. So does everybody see where I got 4 from? So that would be the degree of my polynomial, which would be 4, the number of zeros. And then we want to look at the end behavior of this polynomial. So if the degree is 4, is it even or odd? Even. And is there a negative sign in front of this polynomial? No, so it's positive, even positive. And if you don't remember, the rule for even positive is it ends upward and starts upward. Up and up. And then from here, we're going to find our x-intercepts. So to go from binomial to intercept, we just said equal to 0, which means we get x equals negative 2, x equals 1, x equals 1, and x equals 3. Everybody see where I got those from? You just change the sign because you're setting them equal to 0. Anybody know why I wrote the 1 twice? Does it affect the graph? Yeah, it affects the multiplicity of the graph, meaning at that point, the graph, it's not going to go through that point, it's going to bounce. Very good. And the last one we're going to talk about is the y-intercept. This might be new, but to find the y-intercept of any graph, all you have to do is plug in 0 for x. So I'm just replacing all of my x values with 0. So this will work for literally any graph you ever look at. If you want to find the y-intercept, you plug in 0 for x and you just solve this. And I just use this version, but you could have also used the original and you'll get the same answer. So this would give me y equals 2 times negative 1 times negative 1 times negative 3, which would be negative 2, I just multiplied these two, times positive 3, which is negative 6. So my y-intercept is 0, negative 6. So every function has exactly one y-intercept. So now the next thing we should do is plot our x and y-intercepts. So you're going to go ahead and plot all of them. So negative 2, 0, negative 1, and 3. Looks like that. And then I'll plot my y-intercept, which is at 6, negative 6, so somewhere around here. So that's what your points should look like. Yes?
Why is it
You sure?
Yeah.
Okay. So now from here, we know our end behavior is up, and then which one of these zeros do I have to bounce at instead of go through? The 1. So the 1's not going to go through, it's going to bounce. So we start up because we know it ends up, and it's going to go like this, and then it's going to come here and bounce like that, and then it will go up again. So it's going to look something like this. And you should always check after, once you draw your sketch, and make sure the number of turning points is correct. So we have how many turning points here? 3. Does that make sense with the degree of the polynomial? Yes, it does. Because if you have 3 turning points, the degree should be 4. So what we're going to do now, I think we have one question left. We are going to stop and we're going to finish it up after lunch. We'll do the shorter, this part of the lesson is pretty short, but I do want to make sure we have enough time.